determine the equivalences of a Dealing category between this category of weight modules for this truncated shifted Yang and the category of modules for this metric KLR algebra. And this restricts to the category O here with this positive quotient here. And how does this equivalence work? Well, it's not that complicated. So if n here matches up with m under this equivalence, then the weight space of this n, remember this is a finite dimensional weight space for the action of this guy, will be the same as the sort of idempotent space you get here. Let me explain one thing. So remember I have these idempotents in my KLRW algebra, and they're labeled by two pieces of information. One is a list of the labels of the black strands, and S the position of the black strands. So the positions of the black strands will be precisely the same as the eigenvalues that I had here for my AIPs. But the labels here, this I0 will be, so in total it's some list where I start with some first I1, this is M I1 times, and then I2 and so on. So I pick some ordering on my Dinghen diagram. Maybe this 0 should go up here. Avoid confusion. So I pick some ordering on my Dinghen diagram, and then I just list out the first element of my Dinghen diagram that many times, and the second element of my Dinghen diagram that many times, and so on. So it's some fixed, like, in other words, maybe I should just call this guy 1. Maybe it's 1, 1, 1, 1, 2, and 1 times, and 2 times. So in my idempotent will look like this, where here I have a bunch of strands labeled 1, a bunch of strands labeled 2, and so on. So what's funny about this is that the module here sort of only sees the part of this guy where we have the same, I mean, this M has a lot more parts to it, right, because you could apply other idempotent M with different orders on those strands. But this module here only sort of sees the part where you apply in that order. I'll explain very well. Okay, so that's the theorem, and that, so let me explain sort of the corollaries of this theorem, and then maybe a little bit about a word or two about the proof. So first corollary, this proves an earlier conjecture. This conjecture is from 2 years ago, I think 2015, relating highest weight for lambda mu, and this combinatorics what we call product monomial crystal. So in the special case when G is equal to SLN, so then this Y lambda mu R is this just universal enveloping algebra of GLN modulo this central character. So even in that case, it appears that our result is new. So even in this case, it appears that the classification of simple objects in the category of weight modules for UGLN on which the Gelfand-Sutherland algebra acts, I mean, simply was not known before. So this is our result seems to answer some classical questions. And more generally, it answers questions about weight modules for the W algebras on which the Gelfand-Sutherland algebra acts, simply. And well, 3 is going back to the beginning of my talk. I said that we had this symplectic duality. We had we wanted to relate category O for this quantization of the Avogadro-Riemannian plate with category O for the quiver variety. And I explained that already going from Ben's work, building on Rouquet and Varignon-Vassero, this KLRW algebra is related to the quantizations of the category O for quantizations of the quiver variety. So via these two isomorphisms, we now have the symplectic duality. That's great. And 4, let me get somewhere. I'll bring a board. And 4. So because this KLR2 category acts on this right-hand side, we get that U acts on the left-hand side. Category O is for these guys, but this action we still don't fully understand. We're trying to understand this action. In fact, somehow our earlier approach to this problem was that we actually first tried to construct this action and use the action to build this isomorphism, but that didn't really work, so we built the isomorphism, now we're trying to understand the action. And roughly speaking, to build this action, well, we need to define some functors between these category O's for one guy and for another guy, so there should be a geometric relation between this Avogadro-Riemannian slice W lambda mu and this Avogadro-Riemannian slice mu plus alpha I. So these guys are related, or should be related. I mean, we have some partial results like this, so these guys are related by Hamiltonian reduction. And because of the relation to Hamiltonian reduction, this will allow us to understand this action. So it allows us to construct functors back and forth between category O's here. And so give a kind of geometric interpretation of this action of the KLR2 category. Okay. Now maybe I short amount of minutes. So I just want to maybe briefly explain a little bit about the idea and context of this theorem. So, well, the first point is that actually it fits in a more general picture. So if we have any group G acting on any vector space V, so vector group. In our case, this group will not be the group we're interested in, like the group of the algebra G, but rather some product of GLMIs of related to this. Will be in this case, it happens to be this group. Okay? And this V will be the V of the V used to construct the equivariety. So given such a pair of G and V, in the work of Braverman, Finkelberg, Nakajima, constructed a variety using this G and V called the Coulomb branch. So, let's write Coulomb wrong. So this, I'm not going to get into their definition, but in our case, their definition is you do get this W lambda mu. So you could say generalizing this W lambda mu, and also a quantization. Generalizing this function G. And so, in proving two things which are so contradictory or something, but the first is that to prove this theorem, we don't actually use their construction, but we use some ideas inspired by their construction. In particular, I don't know if I can really say much more. But anyway, the idea is, the construction is kind of geometric. This Coulomb branch is constructed by some kind of convolution, algebra, and homology of something. So we don't use this geometric description of their Coulomb branch, but we use some kind of algebraic ideas coming from their construction. And more generally, Ben, in a separate work, has kind of proved a kind of version of this equivalences that I wrote down here, but for arbitrary Coulomb branches. So relating arbitrary Coulomb branches with arbitrary Higgs branches. So there's this Higgs branch. This terminology comes from the physics. The Higgs branch associated to this pair GV is just the cotangent bundle of V. Take the symplectic reduction, the Hamiltonian reduction by this G. So for arbitrary G, in our case, this Higgs branch would be this equivariety. But for an arbitrary pair of G and V, Ben has an equivalence which is not exactly a special case, but it's similar to Ben's general theorem relating the Coulomb branch and the Higgs branch. I'll stop there.
So apologies, I changed the direction of my talk because I wanted to sort of hear a little bit closer to skein algebras, and so that's what I'm going to do. So quantum character varieties are Azamaya algebras. Before I start the talk properly, though, I want to state an important theorem about the skein algebras, which is a major motivation for what I'll discuss today. Before I get started, also, everything I'll talk about today is joined with Jordan Ganov, who's there, and Pablo Soprano. Okay, so I want to just briefly recall for you the unicity theorem. Did Tangley talk about this as my algebras and skein? No, okay. So unicity theorem for skein, for the Kaufman skein bracket. Okay, so this is the theorem. So part of it is due to Monahan and Long, and then the proof was completed by Froman, Kanya, Bartosinska, and Tangley, who spoke here last week. And it concerns the skein algebra. So this is my notation for the skein algebra of a surface. I won't recall in detail what this is. We had a series of lectures about this last week. Roughly, it's we live on the cylinder of the surface, so as the surface crosses the interval, we draw tangles in there, and we impose sort of SL2 style skein relations, and this has a natural algebra structure on it. And this is, so they study this at a root of unity. Okay. And what they find is that this is an Azamaya algebra over its center. So just the center of this algebra. And moreover, this center is actually just isomorphic as an algebra to functions on the classical character variety. of the surface. Okay, so the picture is that this thing was introduced by Zraev and others as a quantization of the character variety. And then when you specialize Q to be a root of unity, this infinite-dimensional non-commutative algebra inherits a very large central set algebra, in fact a complete center, which is just a copy of functions on the character variety that you started with, and this Azamaya property is the Italo-Locally over the classical character variety of S. The scaling algebra is just a matrix algebra. Okay, so it's called the unicity theorem because when Berhan and Wang first phrased it, they didn't use this. So this is the definition of Azamaya algebra, that Italo-Locally you're just a matrix algebra. So if you think about such a thing, what it's saying is that essentially for every point here, so this is in the center, so if you look at representations of the scaling algebra, for every point here, there's a unique representation because you're a matrix algebra. Matrix algebras have a unique representation. And so this unique representation, Berhan and Wang called the classical shadow. Okay, so they understood this fact about the center becoming completely classical, and they conjectured that there's a unique representation for each point. They called this point the classical shadow, and then this was proved by these three authors, and the proof was using this Azamaya property. Okay, so that's a sort of motivating result for me. I want to emphasize that this is all for SL2, so I should have written that. This is SL2, character variety. And also, these two papers are both appearing in Dimensiones, and I think they deserve to be there because when you try and prove this using scaling technique, it's really, really hard. So they really have to explicitly understand these scaling algebras. They have to explicitly understand the character varieties for these surfaces and produce these central set algebras in a very hands-on way. There's a lot of classical sort of Q combinatorics that goes into the proofs. It's very beautiful work, and what I want to explain today is, so I am interested in a parallel quantization of character varieties, which I'll be talking about this afternoon, and I want to explain a proof that these are also Azamaya algebras in the same sense. And one reason I want to do this is I think the proof that I'll give today is just about, to my taste, a bit easier. It's not by direct computation, it follows from some general principles, and also it works for any gauge group, not just restricted to SL2. So there's a sort of dictionary between these quantum character varieties that I'll discuss today and scaling algebras, and once that dictionary is completed, then we'll have a new proof of these lovely results of these authors. Okay, so without further ado, that's the quantum convenience is section 3 of my talk. Yeah, no, that's exactly how you should think about it. So the first thing I want to do is just recall what I mean here by quantum character stack and quantum character variety. So we had a lecture by Juliet Cook in the summer school, in the winter school, so I'll be a bit brief. I want to talk about roots of unity, the special features of this roots of unity, in particular the quantum convenience. Okay, and then I want to explain the proofs of this Azamaya property for punctured surfaces. So this uses a technique of Brown, Gordon, Poisson orders. And finally, I want to explain what to do for closed surfaces. So closed surfaces are always harder than punctured surfaces for a number of reasons. Okay. So one. So recall, so with Lindsay, to show you, we introduced some categorical invariants of surfaces. Okay, so I'm going to note this. So these depend, depending on a braided tensor category C. Okay, and so this invariant I'm going to denote by ZC. So what I call ZC of S today was indicated like this in Juliet Cook's talk. This notation is a bit cumbersome, so I'll just call it ZC. Okay, so what it does is it maps surfaces and their embeddings and their isotopies to categories and their functors and their natural isomorphisms. Okay, so it's an assignment of surfaces to categories. If I have an embedding between two surfaces, I get an induced functor. And if I have an isotopy between two embeddings, I get an isomorphism between the functors. In a little bit more detail, these are what are called K-linear and presentable. If you like, you should just think abelian categories. It's almost the same. And the functors are what are called co-continuous. Or if you prefer, right exact. Okay, so what that means is that this machine, when we turn the crank, it will always give us some essentially abelian categories, and the functors that it produces will always be right exact. So we can always take right adjoints of any functor we encounter. That's quite useful. And this is a functor of symmetric monoidal two categories. Okay, so the extra information there is that I have a disjoint union on surfaces, and I have a tensor product on categories, and this intertwines those in a natural way. Okay. All right, so because of Dirac structure, I'm going to largely use this as a black box, and I'll just recall for you the properties of it I need as I go. So in the construction, it uses what's called factorization homology. So this was developed by Ayala Francis, following some ideas of Lurie. And so let's write this formula once so that we have some kind of definition. So the invariant that we assign is a colimit over all ways of embedding a disjoint union of disks into our surface. And for each such embedding, we have our braided tensor category C, and we take its tensor product k-fold times. So the picture is, okay, to such a surface, I assign a category, VC of S, and this category is completely determined by probing it by collections of disks. So every time that I give you some collection of disks, then, so here I have 1, 2, 3, 4, 5 disks. So the specification of those disks gives a functor from C to the 5th into here. And so it receives all these functors. So you can imagine sort of testing this thing by shooting disks into it. And each time you do, you get a functor, and it's the universal category that has all that functorial data inside of it. Okay. So I want to emphasize two features of it. So first of all, the empty surface is a surface. So that just means when I said that my category was surfaces, in the Ayala Francis setup, the empty manifold is a manifold. And so what that means, moreover, the empty manifold is canonically assigned just the category of vector spaces over the ground field. That's a sort of basic input. And so what it means is that the empty manifold, including into every surface, gives me a functor from vector spaces to the category that I assign to any given surface. And in particular, if I look at the object, just the one-dimensional vector space here, that goes to a very special object in here, which is called the distinguished object, dist of S. Okay, so I'm going to make a lot of discussion about this distinguished objects in the sequel. And the other sort of formal property that one uses in this business is that if I have a braided tensor functor, functor of braided tensor categories, I automatically get from that data a functor between the invariants. Okay, so the factorization homology is functorial in surfaces, but it's also functorial in the coefficients, which braided tensor category you use. And a lot of the talk is going to be exploiting that. So with Benzi and Roche, we proposed that ZQ of S, which is to say Z of WQG of S, is a quantization of the character stack of S. Okay. By the way, if it troubles you that I keep saying stack rather than variety, I'll clarify that point in a moment. By this, what I really mean by the character stack is I instead consider the framed character variety modulo G, and the framed character variety means I choose arbitrarily on my surface, I choose some fiber here, and I trivialize this fiber. So this, I give an isomorphism of this fiber to G. Or if you like to think about instead pi 1, I'm not quotienting yet by the conjugation action on pi 1, as one usually does. Okay, so that's called the framed character variety. And then whenever I talk about the stack, I really just mean that I'm going to work with this frame thing, which is harmless. It's a smooth. When S is punctured, it's smooth. It's just a nice variety, but I'm going to always remember this G action. That's all I'm ever going to mean by the stack. All right, so okay, in what sense do we propose this as a quantization? So more precisely, so what we showed is that okay, suppose S is a punctured surface. You suppose that S is homeomorphic to sigma G R. So genus G and R punctures with R greater than or equal to 1. Then in that case, we gave an algebra called A sub sigma G R, and an equivalence of this quantum invariant with something very well known. This is okay.